Hello everyone. This week we will cover trip distribution modeling as the second step in the four-step modeling framework. So the aim of trip distribution is to distribute the trips originating in each zone across all the destination zone. In trip distribution modeling, what we do is linking the zonal trip productions, PI, and the zonal trip attractions, AJ. Remember, these productions and attractions were estimated from a trip generation model. Trip distribution modeling corresponds to the stage of travelers choosing a destination for their trips, or as we call destination choice. Let's start with an example. Consider a city with 4 zones. Here in this table, you see an origin destination demand table of the base year, where we can see the total number of trips going between zone I to zone J, for example. And the sum of the columns in each row would be the production, and the sum of the rows in each column will give us the attractions. And the total would be the total number of productions or attractions, which must be equal. We also have a travel time matrix, which gives us the information about how long does it take to travel from zone I to zone J. From the previous two tables, you can get a histogram of trip length distribution. If you look at previous tables, you can see how many trips will be made that take between 0 to 5 minutes, how many trips between 5 to 10 minutes, and etc. So with that information, you can draw such histogram, which we will use later for travel demand calibration and validation. When modeling trip distribution, usually land use will change in the future scenario. The changes in the land use usually reflected in population and employment change, and as a result, trip generation figures are expected to change in the future year. Likewise, travel times are expected to change, mainly because of investment in the transport system or increasing or sometimes decreasing level of congestion in areas where the capacity of the system is not changed as needed. In the trip distribution modeling framework, we also need a future travel time matrix, where similar to the previous travel time matrix, it gives us how long does it take to go from one zone to another, but for a future year scenario. We also have productions and attractions of future as an outcome of a trip generation model for each zone. As I said earlier, the number of total productions must be equal to the number of total attractions. So with that information, the outcome of a trip distribution model is a table as you see here, which is a origin destination demand table for a future year, which tells us how many trips will be made in future from zone I to zone J, where the sum of the rows or the sum of the columns will be equal to the productions and attractions as estimated by a trip generation model. So there are some definitions and notations before diving into the trip distribution modeling examples. TIJKN are trips going from I to J by mode K and by person type N. We can have different person types, mainly representing different income levels, for examples. OIKN is the total number of trips originating at zone I by mode K and person type N. Therefore, the origin destination demand matrix could be represented as a table here, where we have T11 is the number of trips going between zone I to zone 1 to zone 1, or T, for example, 23 is the number of trips being made between zone 2 to zone 3. Where, as I said before, the sum of the columns in each row will give you the productions, or the number of trips that are originated, and the sum of rows in each column gives you the attractions or trips related to the destinations. And that's how this is mathematically represented, where the sum of Tij's over all the j's, which were the destinations, will give you the productions or originated trips, and the sum of the Tij this time over I will give you the Dj, which is the attractions, trips related to the destinations. There are a few other notations which we will use. CIJKN is the cost of traveling from I to J by mode K and by person type N. A small Tijk is the travel time from I to J by mode K. We don't have N here because travel time is dependent on the mode of the travel and is independent of the person type or person income, for example. Pijkn is the proportion of trips from I to J by mode K and person type N. There's also this notion of generalized travel cost function in a travel demand modeling framework, which we will go over now. Generalized travel cost function is a function that replaces travel time. Remember the travel time matrix that we covered in a few slides before? We can replace that travel time matrix by a travel cost matrix which is estimated by a generalized travel cost function, which is represented by Cij. This generalized travel cost function could be a function of in-vehicle travel time, could be a function of walking time, could be a function of waiting time, transfer or interchange time, some monetary charge like toll, traveling from I to J. It could also include parking cost and some modal penalty or an error term. So the first method in trip distribution modeling is a gross factor method. Similar to the trip generation modeling, we can use a simple but a little bit naive growth factor method here. In a uniform growth method, what we do is, if the only information available is about a general growth rate tau for the whole study area, then we can assume that we can apply this general growth factor to all the OD matrix, to every cell in the OD matrix. Therefore, the number of trips between I and J in future, which is represented by capital Tij, will be equal to the uniform growth rate multiplied by each cell in the OD matrix of the current year, which is represented by a small Tij. I think it's a good time now to have a look at activity 5.1 to get a better sense of how gross factor method can be used in trip distribution model. So in this activity, consider a simple 4x4 trip matrix of a base year, which is represented in table 5.2. If the growth in traffic in this study area is expected to be 20% in the next 3 years, it is only a simple matter to multiply every cell of this OD trip matrix by 1.2, representing that 20% increase, to obtain a new matrix of origin-destination trips. So the assumption of uniform growth is very unrealistic, except perhaps for very short time spans, 1 or 2 years. In most other cases, especially for long-term transportation planning and forecasting, one would expect differential growth for different parts of the study area, not necessarily the growth would be uniform across the entire city. The other method in trip distribution modeling is a singly constrained growth factor method. In this method, information is only available on the expected growth in trips originating in or attracting to each zone. So we only have the expected growth whether related to trip reductions or trip attractions. So what we do, we apply an origin or a destination-specific growth factor, tau I, to the corresponding rows in the OD trip matrix to get the OD trip matrix of the future. So for a origin-based singly constrained method, we apply a growth factor tau I by each cell in the OD matrix to get the number of trips in future. For a destination-specific singly constraint growth factor method, we apply the growth factor of the destination-specific factor by the Tij, which is the number of trips in the current year, to get the number of trips in the future year. To get a better sense of how this method works, please have a look at activity 5.2. So in this activity, consider a table as provided below, where we have a OD trip matrix of current year, where we have the trip productions summed up here and trip attractions summed up on the last row. And the total number of trips produced and attracted are equal to 1,635 trips. We also have the origin-specific productions of the future year. So the total number of trips originated at zone 1, when we sum these columns, will be 355 for the current year. For the total number of trips produced in zone 2 for the current year is 455, and so on. But for the future year, the target number of productions is 400 for zone 1, 460 for zone 2, and so on. But we don't have any information about the attractions, which is the sum of the rows for each column. So to apply a singly origin-based constraint growth factor method, what we need to do is we need to calculate a growth factor for each row or for each zone. So the growth factor here would be 400 divided by 355. For zone 2, the growth factor would be 460 divided by 455, and so on. And what you need to do next is you simply multiply the growth factor that you obtained for each zone, for each row, to each cell in that row to get the new values of Tij for the future year. You continue that using the growth factor of each row, and you apply it for the cells in that row to get all the cells completed in the future year OD trip matrix. And what you get next, if you sum all these numbers, you'll get the same number of total productions as you had in your targets. However, interestingly, if you sum the number of attractions, if you sum the attracted trips, it will not be equal to the sum of the productions, simply because what we only took into account was the origin-based growth factors. So we're not expecting, in this case, in this singly constrained method, to get total number of attractions and productions be equal in the target year. The next method in trip distribution modeling is the doubly constrained growth factor method. In this method, information is available on the expected growth in trips originating in and also attracting to each zone. So we will have the trip rates, the growth factor rates for both the attractions and productions. And as a result, we will have different growth rates for trips in and out of each zone, and consequently we will have two sets of growth factors for each zone. How to incorporate this growth factor into the new variables AI and Bj is represented mathematically here, where instead of having a origin-specific or destination-specific or a uniform growth factor, we will have a growth factor that is dependent on AI and Bj, which are the growth factor of the origins and growth factor of the destinations. So to apply this doubly constrained growth factor, there is a simple algorithm which is called biproportional algorithm. We use this algorithm in an example later to show you how it works. But let's quickly go over the algorithm and later we'll see an example. So in the first step of this algorithm, we set all the bj's equal to 1 and we solve the problem for AI, very similar to a singly constrained method. So what do I mean by solve for AI? I mean to find the correction factors or the growth factors AI that satisfy the trip generation constraints. In the second step, with the latest AI that we calculated from the previous step, we solve for Bj. Again, we satisfy the trip attractions constraint this time. And in the last step, we keep the Bj's fixed, we solve for AI, and we repeat the step 2 and 3 until we reach a convergence, or in other words, the changes that we observe in the problem solution are sufficiently small. To better learn or understand how this biproportional algorithm in doubly constrained growth factor method works, please have a look at activity 5.3. In this activity, we will go over the example 5.3 of the textbook. Assume we are given a OD trip matrix of the current year in a city of 4 zones, where we have the total productions and total attractions of the base year and also the future year, target OI and target DJ. So to apply a doubly constrained growth factor problem, we need to apply the biproportional algorithm. To do so, I have created an Excel sheet for you guys to have a look. So in this Excel sheet, we have the OD matrix of the current year as highlighted here. We have the productions of each zone of the base year, productions for the future year, attractions of the base year, and attractions of the future year. So for the first iteration, what we do is we consider Bj equal to 1. So what we do is we only consider the correction factor of the productions. So we calculate a growth factor here, where we divide the target PI by the current year PI. So we get a growth factor for each zone. The second zone, similarly, you get the growth factor by dividing 460 over 455. So after we get the growth factors for each zone, we apply these growth factors. We multiply this growth factor to the cells of each row to get the second table to be ready for the next iteration. So this cell is a result of multiplying the growth factor of zone 1 by cell 1, 1. The second cell is the same growth factor of the same zone multiplied by the second cell. And as another example, the number of trips from zone 4 to 4 is calculated by multiplying the growth factor of zone 4 by the cell 4 by 4. Now that we have this second table of origin destination in the first iteration, we can now calculate a new set of growth factors, this time by looking at the attractions. So we calculate the growth factors using the attractions, very similar to the productions. This time we divide the target attractions by the attractions of the base year to get the new growth factors. Similar to this, it's the target AJ divided by AJ for that specific column. Now that we have the new growth factor rates based on the attractions, we can multiply these growth factors to the associated cells to get a new trip table. So for example, this cell in this new table is coming from the multiplying the growth factor of zone 1 related to the attracted trips by cell 1, 1, coming from the growth factor of zone 1 related to the attracted trips multiplied by the second cell in the table, and so on and so forth to get the entire trip table. So you continue this process in an iterative manner. I again calculate new growth factors, I apply this to the table, I get the new trip table demand, again I calculate a new set of growth factors. I continue this for a few iterations until I reach a state where there is very small difference between the calculated productions and the target productions. So in this case, because my last iteration was based on the growth factors of attracted trips, the attracted trips are equal to the target attracted trips, and there's very small difference between the productions of the base year and productions of the future year. So here was an example of how a biproportional algorithm can be used in a trip distribution modeling. What I would like you guys to do is to go over this example again, try to create a similar spreadsheet for yourself, calculate each cell by yourself to better understand how this method works and to understand how you can implement the biproportional algorithm. There are a few limitations in the gross factor method. The gross factor method is only reasonable for short-term planning horizons or when changes in the transport cost are not to be expected. The gross factor method requires the same database as synthetic methods that we will cover for the rest of the lecture, namely an observed trip matrix, which is usually very expensive to obtain. Also, any error in the base year may be amplified by the application of successive correction factors. So if you have a small error in the base year, because you multiply that by a correction factor or a gross factor in an iterative manner, at the end you're very likely to end up with a big error. Also, if parts of the base year matrix are unobserved, they will remain so in the forecast. These methods cannot be used to fill in an observed cell of partially observed trip matrices. An example is if there is new zones created in the forecast year, for example from zone N to zone M, which we do not have them in the base year, we can't really apply a gross factor because that specific cell in the current year has zero number of trips. However, in the future, they will be having a number of trips going between M to N or N to M. Therefore, we can't really apply a gross factor method to the unobserved cells of the OD demand matrix.